For the following problem, we have a op-amp with our circuit diagram here. We are given a lot of things. We're also given the op-amp power. We need to find the steady state output voltage V out, which is the voltage across the resistor R out. And so our answer is going to be in terms of V out. We need to state the voltage magnitude as positive and state the phase angle as a positive angle as well. This is going to be counterclockwise from the origin, and this will be in the correct quadrant. So taking a look at this, the first thing that we can do is use the node voltage method. Well, we know we have some voltage going in here and some voltage going in here. We know this is going to be Vn because it's a negative and Vp because it's a positive. We know that Vn always equals to Vp. Now, regarding Vp, we can see that this, because we have it grounded right here, is going to make this 0. So this is going to be equal to 0. And since we have current coming out of here, that current is going this way, because remember, current is typically in the opposite direction of our voltage, which is going like this, into the positive out of the negative. That means that this, basically all of this right here, our Vp is 0. And so in that regards, our Vn is also 0. So now we can write out our equation. Starting at our Vn, we are going to have Vn minus V in. And this is all happening over the resistance in and our capacitance in. So we're going to have R in, and we can't simply just do C in because we're dealing with time when we deal with steady state, and so we need to convert this to the S domain. So this is going to be, instead of just ZC, it's going to be 1 over S times C. If we had an inductor, it'd be ZL is equal to S times L. And so we are going to add this because they are in series with each other. If they are in parallel, we would do the whole parallel formula, and then we would just have 1 over SC. Then we are going to have plus. We know that we have some V out right here, right? There's going to be some voltage output, and it's going to be over our R out, and it's going to look like this. And so what we're going to have here essentially is some negative feedback because it's an op-amp going like this way into here. So we are going to have our Vn minus our V out all happening over RF. We're not necessarily very concerned about the R out for this equation right now. This is going to be set equal to 0. Now we know that our Vn for both of these is 0, right? Because it's equal to Vp, which is 0. And we want to solve for our V out, so what we can do is we're going to multiply everything by RF and then move V out to the other side. If we do this, I'm just going to put V out on this side. We're going to get V out is equal to, we are going to have a negative, we are going to have the V input, I'll put these in parentheses, we're going to have our RF because we're multiplying everything by RF, and this is all going to be divided by our R input plus 1 over S times C. And we can't just plug in our values and forget about the S. So what is the S? Well, we know if we were dealing with the transfer function, which we could turn this into, we would say that S is equal to J times omega, with J being an imaginary number, which is exactly what we're going to do right here. So we could rewrite all of this, and it's going to be good to rewrite all of this because what we can do is just substitute for our S the J omega. And now we can plug all of this into a calculator. Well, what is our omega? Our omega, since it's steady state, we can use the same omega that's given right here. And so now, knowing all of this information, we've given everything else, we can plug into a calculator. To bring this down here, I'm going to start plugging in my values. So up top, we have a negative V input. We have our 15 here, and if this is in polar form, our V input's given to us in polar form, so we need to convert it to the rectangular form. And that equation is just in the notes link below the like button very early on. We have negative 15, and since we don't have an angle, we're not going to have an angle here. We'll just have negative 15. Our RF is just the 10 kilo ohms, so we're going to have times 10 raised to the cubed. And then we can divide all of this by our R input, so that's going to be the 10 times 10 raised to the 3 because of the kilo ohms. And then we are going to have plus the 1 divided by the J, which we can represent as I here, our omega, which is 2000, and then our capacitance, which is 0.1 times 10 raised to the -6, because that's what microfarads is. And then we can press go, and we can see that we have our answer here. So we have a -12 minus 6i, with the I just being the j for imaginary number. Now we are going to take this value and we are going to plug it into these equations. Plugging this in, we should get for the answer, approximately for the magnitude, which goes out front, a 13.416 at an angle of 206 degrees. And that is how we would go about solving for this problem.